Hello, there was a student request for me to show how to graph using what I was calling the radar method. The radar method is just a slightly more clever approach than plotting points and connecting them. If you were going to plot points here and connect them, you might choose some different values of theta, which would give you different angles. And for each value of theta, you would work out what was the r, and you would put a point down, and put a point down, and put a point down, and then start to connect them. What the radar method is you're going to choose a couple of key values for theta, put the points down, and then imagine like a sort of animation. So if this is the angle, and the angle is increasing, kind of like a radar sweeping across, the r value is going to be changing at the same time that that angle is changing. So if my finger is where the point would go, let's say the r value starts at 2 right here, and as the angle increases, the r value decreases. In that case, we're going to, as the radar sweeps around, r is going to be going down this direction, so that's going to produce a kind of a curve that way. Okay, so let's look at how you might use that method for this particular equation. Alright, we'll start with theta equals 0. So cosine of 0 is 1, which means r is 2. So when the angle is here, we have a point at 2. Alright, I guess let's think about what happens at pi over 4 here. So at pi over 4, if you multiply that by 2, that'll give us pi over 2. Cosine of pi over 2 is 0. So that means r, once the angle gets up here, r is 0. So that means our point is going from here to there. Well, if you just think about connecting the dots, you're in trouble because you would just draw a horizontal line there, and that doesn't make very much sense. What you need to remember is that r changes as the angle's changing. So if I make my, so this is angle 0, and we got a point here. If my angle is just like a little bit higher, my r value is on that line because it has to be the radius for that particular angle. So here's where it would be if it were 2. Here's where it would be if it were like a little bit less than 2. And then here's where it would be if it were a little bit less. And here's where it would be if it were a little bit less. So this is just estimating some values. These are probably not exact, but it paints a kind of a picture. As my angle is going up this way, my radius is going towards 0, and when I reach here, it is 0. So that's going to produce a kind of a curve like this. Okay, this next section is going to get a little bit trickier. So I know when the angle is pi over 4, my r value is 0. What happens as the radar sweeps in this direction up to pi over 2? This one I'm going to write out. So r of, this is an equation that's r of theta, because r is a function of the angle. So if I've got pi over 2 here, that's going to give me 2 cosine 2 times pi over 2, which is pi. Cosine of pi should be -1, so that means my radius at the angle pi over 2 is -2. Alright, where is -2 if I'm pointed this direction? +2 would be up here, so -2 is the other direction. So this is where my point is going to end up. Well, again, we have a hard connecting the dots problem. When my angle was this direction, I was at 0. When my angle is straight up and down, I'm there. But again, you don't want to just connect the dots straight from here to there. You have to think about what's happening as the radar is sweeping across. So, let's imagine just increasing the angle a tiny, tiny bit right here. So my radius was at 0. If I go up a little bit, I know that my radius is going from 0 down to -2. So my radius must have gone down by a little bit. So that means it's like a tiny bit negative. Alright, well if the angle's here, where is a tiny bit negative from there? If I kind of extend it out the other way, it must be like a little bit here. And if I move my angle a little bit more, here's the line as I extend it the other direction. So it's a little bit more negative, so that means it's right there. If I move this up a little bit, it's a little bit more negative, so it's like there. So now you can start seeing where the dots are going to connect. They're going to go around this way. Okay, what happens as we continue to sweep the radar in this direction? I know that it's going to go back from -2 to 0 again. So that means as my angle sweeps from here to here, I'm going to have negative values going back to 0. So as you continue to sweep this around, it's going to make a curve like this, and then the curve is going to go around here, and then the curve is going to go around there, and then the curve is going to go around here, and there, and here to complete the kind of four-leaf clover. You can verify that that's true in Desmos. Here's what it looks like in Desmos, which is what we had. What I want to get at is this process of thinking about key values and then how to connect the dots. Don't just plot a point, connect them. Remember that the R values only change as the angle is moving. So if you imagine the radar sweeping around, and that's the point on the radar as it's moving. I'm going to animate it now. There's going to be this green line, which is represents the angle as it's moving. And then here's the orange dot, which is going to move along the curve. So let's imagine the radar sweeping from an angle of 0 to an angle of pi/2. So here we go. As you can see, the distance, so watch the distance of the orange dot from the origin along the green line. Here it's 2. Now it's a little less than 2. So if you just watch that distance, the distance is going down until eventually here it's 0. Okay, now we're going to go from an angle of pi/2 up to here an angle of pi. So here the dot continues to go down into quadrant 3. And the reason why is because R is negative. So even though the radar continues to sweep up towards that positive y = 2, the dot is sweeping down in a negative direction. So here at an angle of pi, we've got a radius of -2. And then as we continue to sweep it, it's going from a negative R value back to 0. And now we're going to go from 0 to a value of positive radius. Okay, you might be thinking positive, wait a minute, we're at x equals -2. Remember, it's the radius that's positive here. So you have to remember what direction is the angle pointing. Here, I wish I could put an arrowhead on this, but the angle is pointing, this was at 0, so the angle's pointing off to the right. And here the angle's pointing up. And here the angle's pointing left. So when R is positive, we mean a positive distance towards where the angle is, which just happens to be into -x because the angle is pointed into the second quadrant there. Okay, we could change this to, like, let's make this, I don't know, just something big. So let's watch a full animation now. When I press play, you see the dot kind of sweeping around there. And as the angle continues, it's a periodic function, of course, so it's just going to continue to do that until it hits my angle of 12, and now it's going backwards. Okay, good luck thinking about this. Oh, by the way, if you want to make your own versions of this in Desmos, Desmos doesn't do both polar and parametric at the same time. You can make a parametric equation as long as you're using rectangular coordinates. So all I've done is I've taken the polar equation and converted it into rectangular coordinates using the equations that we thought of in class. So here you can see in the left, I've got my R value is a function of a variable. I didn't write theta because theta is kind of a special thing. I just wrote x here, but that's just a dummy variable. That could be anything. I could call that b, and it would work just fine. And then you know that the x-coordinate is r times cosine theta, and the y-coordinate is r times sine theta. So that's just the conversion into rectangular coordinates. And now I'm using this parametric approach that we know in order to graph that. Okay. Oh, and then my line here, of course, the line is just the slope to where that point is, and it's just a regular kind of rectangular line equation. Okay, good luck.